to the last day and last session, that is tutorial number 4. So we had a very busy, hectic, and enjoyable day for enjoyable schedule for last 5 days. So this is the last session. After this, you will be having an exam of 1 hour duration. There will be 50 questions of MCQ type, multiple choice questions. Okay. Then after this evaluation also, you will be given a grade card. Okay. Grading will be done. You will be given a grade card for this. So you have to appear that exam. It's a mandatory part of this. It is there in the schedule. So after that, at the end, we'll be having a valedictory certificate distribution. Then you will, before that, we will be taking your feedback about this course. So give your transparent feedback. Anyway, so last one. So we have now done so. We have learned so many things about microfabrication and devices. There were in total 4 experts. I have got one foreign expert and an Indian expert. Yesterday, you listened to him from IIT Kharagpur. Then Dr. Sunil Kumar D. Even I also talked something. So just to combining them, what are the key challenges in microfabrication and devices that is being faced today? Now, the key challenges: limitations in achieving high precision and accuracy at decreasing scale. Now, it's a general rule that 100% accuracy is never achievable. Okay, it's a thumb rule because you cannot go for 100% accuracy. That's why we go for some tolerances and we give some allowances also. Okay, so these tolerances and allowances, depending on that, depending upon our use, accuracy. So obviously, if you go for more accuracy, cost will be more. Okay, and it goes in an exponential manner. Okay, so if we want high accuracy, then the cost will increase exponentially. Okay, and again, there are things. Suppose I am manufacturing a table, say. So for a study table for my kid, so I not be having that accuracy. Maybe about dimensional accuracy or surface finish, whatever. I can go tolerate up to, say, I want it is 100 centimeters, say. So if 1 centimeter plus or minus, okay, I can tolerate with that. But if this be a component which has to be used in spacecraft or maybe some your engine part, so it will be a very big problem for us. So depending upon your use requirement, so we depend this precision and accuracy. And precision is you have to be very precise in that. Again, depending upon material also, what material you use, what method you use. So your precision and accuracy both depend on that. So it's the greater limitation for achieving high precision and accuracy because these are all up to micro, nano, major scale. So for that, you require this. So this is again a challenge for this. Then difficulty of fabricating complex 3D structures. Okay. So again, 3D printing also, yeah. But in that case, some intricate structures, okay, some complex structures, it is difficult to prepare also. Then, as I told already, material property limitations. So, certain properties, it may be mechanical property, it may be electrical property, it may be its thermal property, anyway. So, whatever property I want that is required for me, all these properties I cannot get in a single material. Okay. So, sir has already told you in the morning session, Professor was telling about your active learning method for screening material. Okay. Now, there are also usual methods for screening here that is as good as your grading is awarded. Okay, for different courses. Suppose in a semester we are running say 5 courses. Okay, so depending on its importance, we assign some credits to them. Maybe some paper will be 4 credits, some will be 3 credits, some will be 2 credit, like that. So depending on that, the paper having 2 credit and the paper having 4 credits, so obviously 4 credit means the subject has got more importance. Okay. So depending on importance of the subject, we assign some credit. Then after evaluation, you will be assigned a grade, maybe on a 10-point scale. Suppose in a subject you have got 10, on somebody else might have got 9, 8, 7, like this. So what do we do? So whatever you are obtaining, that is being multiplied by the credit, and the sum is taken up, divided by the total credit, gives rise to your total score, average score. Similarly, here also, suppose I have got say 5 candidate materials, okay, and I have say 10 properties I require. Okay, the properties, maybe its ductility, say one of the property, thermal conductivity may be one of the property, surface roughness is one of the property, cost is another property, availability is another property. Okay, so to all the, again, out of all these properties, again I have to grade which one is the most important property. So to that I'll assign a grade. Okay, more grade will be given to more important property, less grade for less important property. Okay, then like your credit. Okay, so we'll give credits to those properties. Then I have got certain candidate materials, maybe silicon or iron, copper, gold, plastic, wood, whatever. So then I'll give them marks. In conductivity, who gets the first one, whether gold or copper or iron or plastic or wood, whatever. So I'll assign them mark. Okay, in that say 10-point scale, if I take, then for other properties also, we'll assign marks like this. So after this, just as different students are graded, they get a final grade. So the awarded grade to each candidate material is multiplied to its credit. Then the sum is taken, divided by the total credit, will give rise to this. Again, these are all we can assign some marks, but there is something which you cannot assign marks. Like say, suppose for something I taste, whether it tastes good or not, or smells good or not. So for that, either I'll go in a digital way. If it smells good or tastes good, I'll assign it 1. If it is not good, I'll assign it 0. Okay. So in that also, like accept or reject, in that sort of thing, we go for all these to which we cannot assign any credit. Anyway, so what I meant to say is, whatever properties that is required for me for the fabrication, all the properties may not be available with a single material. There may be different suitable candidate materials. So out of them, I have to choose the best. So then again, issues with the cost, availability, and cost factor we have to see. Like for me, a wood, for my baby for reading, a wooden chair will do, or a plastic chair will do. I may not go for preparing it out of gold. Okay, so cost part also. Throughput, I was just explaining you the other day. Throughput, it is a little bit different from profit. Profit means that is your selling price minus manufacturing cost. But again, throughput is something that is the selling price minus raw material cost, because whatever is there after you deduct the raw material price from the selling price, that you utilize, or that part you have to optimize this. So you have to get the best throughput, so that your production cost will be low, you can utilize your resources successfully. Then testing also, after that is being produced, tested. So whether you will go for destructive testing or NDT, non-destructive testing, then again, if you, or That testing and simulation, it can be taken apart from the laboratory to computer also. Through modeling simulation, you can go for testing also. So these are the general challenges. Then difficulties in microfabrication and devices. What are the difficulties? For ensuring reliable. Then what is reliability? Reliability is the satisfactory working of any device for its for a prolonged time as it is desired for. That means, say I am purchasing a bike, and let us say its general life period is 15 years. So it must give me satisfactory output or performance for its intended life for which it is meant for. Okay, that is your reliability. Then managing high energy processes. Okay, so sometimes your for setup cost will be very high. You require high energy for that. So it's a difficult task to manage those high energy processes. Then developing advanced clean room technology for contamination control. So mostly this thing, the microfabrication, it occurs in a clean environment. Okay, dust proof environment. Even we are also habituated coming into this room without shoes. Yeah. In the other day, last day, you have listened Professor Mukherjee. He came with chappals and he was telling, okay, I'm habituated because in my lab also so many work is going on. So we used to wear another socks while entering into this. Shoes are not allowed, chappals are not allowed. They use different chappals because it has to be manufactured. The manufacturing process should be in clean environment. So I'm habituated, so I forgot wearing shoes. So I came by sandal. Anyway, so again, this is also a difficult task, developing advanced clean room technology for contamination control. Because even a teeny dust particle, if that is being deposited, say your silicon wafer, while or in that solution, if that is being diluted also, or maybe your virus, bacteria free, it should be that environment. Otherwise, it will be contaminated. So in small scale, it affects a lot because even the size of a, I mean, we are working with the size which is less than the size of a bacteria also. Okay, so you need to have a clean environment and known as your clean room technology. So it should be contamination free. So again, it's a costly affair to have get that environment. Then integrating these micro devices with macroscopic system, because the small devices that you are manufacturing, so they are to be finally integrated with some macroscopic device, macroscopic system. Then if I classify it, precision and accuracy, the difficulty as we are discussing, dimensional control. Okay, this precision and accuracy. Precision means how close you are to the desired dimension while manufacturing. Suppose even if I manufacture, suppose 10 components of this part. So these 10 components may not be exactly the same. Okay, maybe with same machine, same I'm producing this. Because as I told, it's a thumb rule, 100% accuracy is never achievable. So maybe it may be produced by same operator or different operator, or with same machine or different machine. So there are several factors affecting this. Hmm. There may be backlash error in the machine, or there may be, it depends on your mindset on which environment you are working. Then the skillness of the person who is working, then the environmental condition that you are working. If you require, I mean, more accuracy, say suppose I am working in an environment of say 45 degrees centigrade, somebody is working in 10 degrees centigrade. Obviously, for that, hello. Huh. Some micro elongation will be there due to that temperature also. Temperature dip. So as features get smaller, maintaining extreme precision and accuracy, it becomes difficult, requiring advanced techniques and equipment to meet strict tolerances. So, I mean, if the machines are big, it will give different types of error. Again, wear and tear error might be there also. Then uniformity. Ensuring that microfabricated devices have uniform characteristics and performance across large areas, it's a complex task and it's a challenge also. Next is material and design. So, material limitations, finding and processing materials that are suitable for microfabrication and exhibit the desired mechanical, thermal, and functional properties at the micro scale is a significant hurdle. Spec- No, I may not have brought. Okay. Anyway, so material limitations are there because as the same thing we are discussing, your desired mechanical, thermal, functional properties in micro scale level, it's a hurdle because you cannot get all those with single material. There may be different alternative materials having different property. So geometric freedom. So your subtractive processes are often limited to 2.2D or 2.5D structures, making the creation of complex high aspect ratio of 3D design difficult. Here the 2. I mean, it is in between 2 dimension to 3 dimension manufacturing. Size effects. At micro and nano scales, material properties can deviate from bulk behavior with changes in crystallographic anisotropy and surface to volume ratio impacting device performance. So, sir was telling about this, how volume varies in linear scale also. You can take him out. Feeling cold, no? Next. Then manufacturing and cost. What's the challenge associated with this? High cost. So initial investment in specialized equipment and clean room facility. Again, I was telling about clean room. It's a very costly affair. Clean room facility can be a substantial barrier, especially for smaller companies or researchers. So, in though most of the researchers they know the theoretical thing and yeah, but doing experimentation due to funding constraint, due to this cost factor. So it's very difficult task to have this facilities of equipment and clean room. Throughput, achieving higher throughput, the amount of product manufactured per unit of time, it is a persistent challenge, especially for processes that require high precision. Then complexity. The intricate nature of microfabrication processes requires specialized knowledge and skills, contributing to the complexity and cost of the technology. So, mostly your microfabrication processes that are intricate in nature, which requires special knowledge skill also, and due to their due to the intricate process, it becomes complex and it adds to more cost. Then testing and reliability. So silicon wafer we're discussing, wafer level testing, testing microfabricated devices at the wafer level before dicing and packaging presents unique challenges as bare die performance can differ from packaged devices. Then reliability and fatigue. Ensuring the long-term reliability of micro devices is crucial as they can be susceptible to issues like fatigue and degradation under operating conditions. Now, next challenge is integration and cleanliness. So, first, interfacing with the microscopic world. So, integrating microscopic devices with macroscopic interface for electronic optics and fluidics is a complex engineering task that requires overcoming interface barrier. Then clean room technology, microfabrication demands highly controlled clean room environment to prevent contamination from dust, microbes, and other particles which can compromise the device quality. Then again, there's another here, same thing. It is broadly we can classify process related challenges, material related challenges, then device related challenges. Under process related challenges, lithography limits, etching difficulties, the material coming out by etching process, then aligning it, alignment errors, then yield and reproducibility, then clean room requirements. They all of them they come under this process related. They're all process related challenges. Then material related. So we are just summing up what we have discussed. There may be material defects or thin film stresses. Then contamination control, interface quality, new material integration, and device related. We'll be going in detail into this. Device related challenges, scaling issues, heat dissipation, power leakage, reliability and aging, then packaging challenges. So, economic and so challenge, we put it in a flow chart form. Economic and environmental, testing, packaging, device level challenge, process challenge, material challenge. So these three were there. Then testing and packaging. Also there may be economic and environmental challenges. Now material challenges, defects and impurities. Even teeny impurities can drastically affect electrical and mechanical performances. That is why you require a closed room. Yes, these impurities, these are inside the material. Okay, like it may be blowholes or some foreign particles might be there. Material compatibility, integrating metals, semiconductors, and dielectrics with different thermal and chemical properties. Then stress and strain. So thin film and multi-layers can wrap, they may crack or they may delaminate. I mean, one over the other, delamination, and the layers may become squeezed or they may become open also. So that is your delamination due to residual stresses. And novel material. So emerging need of two-dimensional material like graphene or MOS2 and wide band gap semiconductors, GAN or silicon carbide SiC face, they all these face fabrication difficulties. And process challenges, lithography limit, extreme miniaturization require EUV lithography, which is very costly and complex. Then etching process, achieving high aspect ratio and anisotropy without damaging underlying layers. Then deposition control, uniformity at nanometer thickness across large wafers. It is also difficult. Clean room environment, any contaminated dust particle can ruin the device up to large extent. Then device level challenges, that is scaling laws, power and heat management, reliability, integration. So scaling laws. As dimensions shrink, Moore's law, in the very first class, first lecture, you have known about Moore's law. Okay. So due to miniaturization, dimension shrinks, short channel effect, leakage currents, and variability increase. So, power and heat management, removing heat efficiency from densely packed devices. Reliability, devices degrade due to electromigration, dielectric breakdown, and mechanical fatigue. Then integration, combining MEMS, CMOS sensors, and photonics in a single chip. Testing and packaging challenges. So testing challenges also we discussed. At micro and nano level, nanoscale, it is difficult to probe without damaging the device. Packaging, protecting fragile microstructures while maintaining the performance, that is hermetic sealing or interconnects. Then yield and scalability, that is defects at such small scale lead to yield loss, increasing cost. Then economic and environmental challenges, high cost of fabrication, obviously your clean rooms, UV lithography machines, and advanced tools, they are extremely expensive. Energy consumption, your semiconductor fabs, they are energy intensive. Sustainability, chemical waste, water usage, and rare material consumption pose environmental concerns. So, the summary is we have challenges in material, processes, device physics, packaging, testing, sustainability. So, in materials, we know about purity and its compatibility. Then in processes, lithography and etching. Then device physics, scaling and power, packaging, testing, and sustainability. Okay. So, any question? Okay. So, we'll all take you to our labs now. So, we'll be moving there. You will see how it is maintained in the lab. So, then after that, we'll be having your examination. So, thank you.